Awesome.
Cool. Okay. So I guess before I prepared some slides. So I'll bring those up in a minute, but before when I do that, I won't be able to see you guys quite as well. So before I do that, I guess a couple things I wanted to say. So I figured I would talk about one kind of recent direction in our group. It's indicative of, I think, some of the things I was seeing on the slides that Karen had up just before, just before I joined. So about inverting games, but I'll try to give at least like a very, very quick overview of some of the fundamentals beforehand. But I intentionally made this slide deck pretty short, so I want to have time for questions during. I also have my iPad and pencil here, so if we want to get on the board, basically, I would love to do that. If you have sort of more sort of questions, we can dig into any of these particular directions that come up. And the other thing I always like to do before giving these kinds of, or at least guest lectures on these topics, I want to kind of quick poll you guys just to get a sense of what folks' background is. So can you maybe raise your hand if you're a first-year PhD student or a master's student? Okay, and I guess everybody else is second or later year PhD? Okay. So raise your hand if you've taken some kind of optimization course. Okay, about half. And for those who raised your hand, I assume it was a convex course, but was it not a convex course for anybody? Like an algorithms course or something like that? Raise your hand if it was a convex course. How about that? Okay, so, okay. All right. And I'm assuming, if you've taken a game theory course, can you raise your hand? Oh, okay, cool, awesome. Okay, great. So what I'll show you is basically like a optimization themed viewpoint on some class of games. So it's definitely a subset of the field of game theory. If you've, for the, I guess the one person who's taken game theory course, you may have seen some of this, you may not have seen it, I'm not sure, but most courses that I'm familiar with kind of teach it from a bit of a different perspective. So, so hopefully this is a bit fresh. And I guess we can go ahead and get started. Let me share my screen. I think this will work. If I go here, yes, perfect. You see the correct screen, not the presenter view.
Yes, we see the full screen.
Great, fantastic. Okay, so I guess the starting point that I always like to start with this slide is just to say, hey, basically wherever application areas you care about, whatever it is, if it's transportation, if it's power, if it's routing, if it's something more abstract, like maybe like I don't know, social networking, market design, whatever it is, you can, as long as there's multiple decision makers, each kind of optimizing for something, and the interactions kind of matter, then it's reasonable to talk about a game. So it doesn't have to be a game like chess, board game. You can have games show up everywhere. And for the sake of this talk, and I think a lot of the ideas that I'll introduce, I think it's really helpful to think about games that arise in autonomous driving, just because it's very easy to have intuitive feelings about what equilibria are, because everybody's been in these kinds of situations. So think about the picture on the left. If you're this car and you're trying to decide what to do, probably the most common thing that, if you ask somebody in a self-driving car company, at least, when I was interning in one of these places, the most common thing that people would do is some flavor of model predictive control. Would look basically like the problem I'm showing you in the center. Let's say that X is the state of the car over time, bold X. The kind of control actions that you're commanding or you're planning to command into the motor and the steering and whatever, that's U, bold U, so kind of sequences of actions over time. What you would plan to do is basically choose a sequence of actions U that minimize some objective function J, subject to some constraints that encode, for example, the vehicle dynamics. That's what I'm showing with big F, and maybe starting at a particular known location, X hat. You could have other constraints, but some flavor of a problem that looks like this. There'd be an optimization problem with some constraints. You know, the kind of next obvious thing to realize is that actually the problem, like in this case, the objective that you would want to optimize for as the driver of this, you know, black sedan would be probably dependent on what you think other drivers are going to do. So if you're agent one here and you'd like to make a lane change, you know, what you think of the quality of that planned lane change should depend on what you think the other agents here, agents 2 and 3, are going to do in the future. So like if you think that agent 2 is going to start pedal to the metal accelerating, then that, you know, you may think that that will cause a collision. Whereas if you think that agent 2 is not going to accelerate very much, then maybe your lane change is just going to be fine, and J would be some small number that you like. So the point is, the objective you have is, you know, generally going to depend on what you think others are going to do. And the next logical kind of conclusion to make is that, well, you know, I'm not the only decision maker here. Agents 2 and 3, or all the other cars on the road, are also decision makers. And so really, they're solving some kind of similar problem to what I'm solving. And so where do these X2s and X3s come from? Well, they come from the planned decisions that agents 2 and 3 are choosing. So what I've done here is just kind of copy pasted agent 1's problem and done it 2 more times and changed the labels. So agents 2 and 3 have their own versions of these problems. And as soon as you kind of realize that each agent's decision impacts the other's objective in some way, you naturally kind of found a game. So this is like, at least to me, the most intuitive way to see games starting to arise in kind of non-trivial sorts of settings, like outside of board games. So you could do this. You could, you know, if we could solve problems like this, then you might basically use them to plan trajectories in just the same way you would use model predictive control, just as a kind of example. So anyway, hopefully this communicates a bit of where games can arise. Obviously, they could be well outside of these sorts of transportation settings, but I think it's nice and intuitive. So before I move on, are there any questions about this general setting?
I think it looks good on our end.
Okay. Cool. So I'll give you a very quick just rundown on like how one would go about solving these problems. I think the first thing to say before I show anything else is to say these are generally very hard problems to solve. So in general, the results are like not good from a computational complexity perspective. So if you want to actually find an honest to goodness solution to one of these problems, and I'm not yet telling you what kind of solution I'm talking about, but in general, like let's say a Nash solution. If you want to find a Nash solution to these problems, in general, it's not easy. But often, and this is kind of the perspective that I've certainly adopted in my group, but I think a lot of other people would agree, often it's okay to look for a kind of some kind of relaxation of the proper kind of the proper solution concept. And it turns out that if you're willing to cut a few corners that I hope I can convince you are reasonable, then it's actually quite easy to solve these problems. So let me kind of show you what I mean. So like if we go back to these coupled optimization problems, I've rewritten them a little bit. The superscript i's are for player I. There's capital N players. The blue X not I. This is just saying all the players besides I. So I'm kind of just trying to tell you, hey, player I is optimizing for its own objective, depends on all the other players' actions. There's some constraints that are specific to player I. That's what this is saying. If we look back at all these problems, then kind of what's true here is that at least to first order, and again, I haven't really told you what a Nash equilibrium is, but at a Nash equilibrium point, which is just a point where basically everybody is unilaterally happy, then what should be, you know, what definitely should be true is that all players' KKT conditions should be satisfied. And so what I can do is kind of just transcribe the KKT conditions for all the players. And I've done that here. So what you have to do, if for those, I guess, was it 4 or 5 people that had taken an optimization class, something like this will look familiar. You introduce Lagrange multipliers for the constraints. So that's these lambda variables. I guess I didn't ask if anybody taken an optimal control course, but if you took an optimal control course, just call this a costate and it's the same thing. So basically these lambda variables tell you what the price of violating the constraint is for each player at optimum. So anyway, there's, subject to some conditions we're not going to talk about unless you want to, there's a unique set of Lagrange multipliers associated to these problems. And so anyway, there should be some function g of all the variables x2 lambda such that a bunch of stuff is 0. Okay, and the bunch of stuff is, again, this is, I guess, for folks that have taken the optimization courses, all I've done is I've said I've taken each player's Lagrangian, taken its derivative with respect to that player's variables. So that's like if, I guess I can't see my mouse, so I guess you can't either. But the first 2 rows, I'm taking gradient of player 1's Lagrangian with respect to player 1's states, and then with respect to player 1's actions. Those are the first 2 rows. The third row is basically saying player 1's constraints should be satisfied. And then I'm dotting, doing the same thing for all the players. Anyway, so to first order, like these are necessary conditions for all players to be happy. So, so what we can do is kind of stare at these conditions. And if we stare at them, what we're going to realize is forgetting the big nasty nonsense in the brackets, there's just some function of some variables is equal to 0. So in order to find a solution, it's just a set of xu lambda which satisfy the equation. It's a root finding problem. Okay, so that's kind of the basic building block. There's a quick subtlety I'll point out just because it's kind of close to my heart. I love talking about this. Actually, if you solve these problems, what you find is called an open loop equilibrium. It's basically just an open loop sequence of actions for each player. And anyway, there are some contexts where that's a good thing to find. If you've taken a control course and you hear the word open loop, you probably immediately start to cringe. There's a good reason why you should cringe. These are not always the right thing to find. So often what you want is some kind of feedback policy that solves the problem. And so if you actually want to find that, we've done some work on that, but it ends up being a lot more complicated to talk about. So I'll just kind of stick with this simple, relatively simple open loop problem just for this rest of today. But I'm very, very happy to tell you about the more complicated picture. So anyway, this is the building block we're going to use for the rest of today. If I see a game, I'm immediately going to think about writing down KKT conditions for all the players and finding a set of states, actions, and Lagrange multipliers for all the players that satisfy the equations. Okay. So I guess the last word to say about that is that it's actually very fast. So for problems that arise in trajectory planning and stuff, here I'm showing overview of one of the tests that I ran as my last couple months of PhD was coded up a version of this kind of solver, put it on an airplane. We're taxiing around the airport trying to avoid taxiway intrusions and modeling those as games. Long story short, very, very fast to solve these types of problems. So, so this is sort of harking back to what I said earlier, in general, the problems are really hard to solve, but if you're willing to just look for a KKT point, which is only first order optimal, it's very, very easy. Okay. All right. So with all that said, I'm going to tell you about the recent work we've been doing. It's a bit of a strange title, and all credit should go to the 2 kind of student authors, Shinjae and Lasse, but I'll try to do their work justice here. So just to unpack the title briefly, what's happening is that the last word, obviously, we're going to talk about games. Working kind of backwards, we're talking about inverting games. So I'll explain what I mean in a bit, but inverting a game is if you've seen inverse reinforcement learning problem, maybe Karen has talked about that in this class. It's basically the same idea. I don't know what problem, if I don't know what problems players are trying to solve, how can I figure out what their objectives or maybe their constraints are from watching gameplay? So that's the type of problem we're going to be talking about here. And then the rest of it is just some nonsense talking about Bayes rule. So that's the plan.
Yeah. So David, real quick, right before you came on, I was giving a quick overview and grabbed a lot of screenshots from your papers on some of these equations. So I did briefly mention inverse games, but it was like very quick. So just to help for some context.
Cool. Okay. Well, hopefully what I'll show you will be put some of that in some maybe some more detailed context, I hope. So so anyway, there's one other like key observation that's gonna appear in just a second. So I want to give you the I want to explicitly build that up here. So so turns out that Nash equilibria are basically they're differentiable with respect to parameters of the game, subject to some assumptions, of course. But what this means is, let's say there's some hidden parameter of a player's objective. I'll show you in more detail on the next slide. But what this means is that I can compute the derivative of the Nash equilibrium of the game with respect to that variable. So if like player one's objective changes by a little bit, assuming everything is, basically subject to some differentiability assumptions on parts of the game and some other assumptions, then I can differentiate the solution with respect to the parameter. So that's going to be a really important kind of technical ingredient in order to build up the framework we'll talk about. And the basic way I'll show you how this works on this slide and the next one is just kind of goes back to this, like, at least I remember seeing this in, I don't know, like high school calculus. Basically, I have the equation of a circle and I ask you, what's the slope dy dx? How can you find dy dx? Well, you can implicitly differentiate the equation x squared plus y squared equal 1 with respect to x. So if you do that, you get 2x dx plus 2y dy is equal 0. Rearrange, and you get dy dx is minus x by y. So it's like a kind of a clunky fake math way to see what the correct answer, but the basic idea is you can implicit differentiate. There is a function implicitly specified by the equation x squared plus y squared equal 1. And so if I find any point xy on the circle, in the neighborhood of that point, this equation specifies a function implicitly, and implicit function theorem tells me how to get the derivative of one variable with respect to the other in that neighborhood of the point xy. So that's what's going here. So the picture is like if I pick a point xy that's on the top left of the circle, draw the tangent line, this would give me the slope. Okay, so how does that apply to games? Let's say now that the solution of the game is tau x u lambda, and it depends upon some parameter theta. Well, if I kind of push that theta into all the places it could possibly appear, it'll be something like what I'm showing at the right. There's a function used to be just gx u lambda, g tau. Now I'm adding a parameter theta to the function g, and it's showing up in all the places on the right-hand side. So don't worry too much, but basically there's a theta that's now parametrizing all of the terms. If I want to, differentiate tau with respect to theta, implicit function theorem tells me to basically play a trick like this. Take dg d theta. The total derivative with respect to theta should be 0 on this manifold g equals 0. And so the total derivative should be the partial derivative with respect to theta plus the partial derivative with respect to tau times d tau d theta. So chain rule. And rearrange, and you get the thing I've shown here. And there are some caveats, like I don't want to get too wildly into the details, but there's a few caveats. Anyway, long story short, subject to the caveats, you can differentiate tau with respect to theta, and that's how you do it. Okay, so now that we have all the groundwork, let me show you the inverse game problem that we're interested in solving. So running example we'll work with is just intersections. So if I'm AV entering this intersection, I see some human-driven car. I'd like to model the human as solving a game with me as the other player. So I'm trying to imagine what is in the human's head. Well, so basically what I need to do is I know my goal. I'm trying to go straight. I don't know what the other guy wants to do. So if I kind of imagine the parameter theta now is where does the human driver want to go? So it's just a point in R2. Then, once that thing is specified, there's a game. I could solve the game with the tools I showed you before. And kind of that constitutes some plan for myself and some prediction for what the other guy's going to do. So if I knew theta, I could solve the game in kind of forward mode and get a set of trajectories for the players. The one corresponding to me would be my planned trajectory. The one corresponding to the human driver would be what I think he's going to do in response. But if I don't know what theta is, I don't know what the other guy wants to do, I don't know where his goal is, then what I can ask myself is if I've seen them act, so that's like these observations, y, then can I back out what theta is? Can I invert the game problem and figure out what is theta? So I think what Karen was showing you, if I recognized the equations just before just as I was signing on, there was something that looked like this. So the kind of natural thing that at least we've studied and several other folks have studied too is framing this problem in kind of like a maximum likelihood sort of way, which is essentially to say, come up with some likelihood model for what sensor you have. That's like py given tau. So like if the actual trajectory driven by the drivers was tau, how likely would be the data that I saw? Phi. And just solve that maximum likelihood problem, but constrain yourself to choose a tau, which is a Nash equilibrium of the game theta. So you're trying to kind of jointly choose tau and theta in order to maximize the likelihood of the data. So fine, you can do that. The problem is that is just going to give you a single kind of best estimate, maximum likelihood guess of theta. So in this paper, if you do that, like the way to actually do it would be to replace this condition with the g tau theta equals 0. Anyway, so but in this paper, in this talk, what I'm gonna tell you about is kind of fixing this like point estimate problem. So in other words, rather than just getting a point estimate of what my best guess of what theta is, for planning purposes, like for actually making decisions based upon a model of a game, it would be nice if I could recover a model of uncertainty about what I think the other player's objectives are. So in this case, like the way to write that down is just, I would like to have a posterior p theta given y. So in this case, like, let's say I see this human driver start to turn to the left. I would like to somehow be able to figure out that the most likely goals for the human are, that they're basically either trying to end up somewhere on, the lane on the right-hand side or somewhere in the lane in the center on the bottom. And I'd like to have some probability densities on those things. So that's like what we're after here. We're after those densities. And once we're given those densities, maybe we could use them in some kind of fancy planner to account for the uncertainty. So that's sort of why we're interested in. There's a few things that make this problem hard. So I can write down Bayes' rule. That's easy enough. But the first challenge is that the prior is unknown. So if anytime I'm talking about a posterior distribution given some data, I need to know what the prior on the parameters are. So like I don't, what should I plug in here? I don't know the prior necessarily. The second thing is actually figuring out what observations I expect to see given a set of parameters requires solving the game. So that's, we saw that that's basically a root finding problem, but it's still, a bit complicated, I guess. And the last thing is just this like marginalization in the bottom. It involves integrating over all of the possible values of theta. And so if theta is like here, it's a point in R2, that's maybe not so bad. I guess numerical integration is okay. But if we get into higher dimensional problems, like maybe there's more players, then this could get really bad. So anyway, those are the three problems. But there is like a nice observation, which is that actually for planning purposes, I may not actually need the full posterior. Like maybe it might be enough to just be able to sample from it. And so I'll show you. Actually, I guess I can go ahead and describe like how are we going to use this? What we're going to end up doing is showing that like if all you can do is sample from the posterior, how you can use that ability is then draw a bunch of samples and then basically cluster them into a few clusters, let's say, and then basically kind of come up with the most likely values of theta that agree with the data and their corresponding likelihoods, and kind of solve like a finite version of whatever planning problem you're dealing with. So let's say you're trying to plan a sequence of actions for the AV that is like best in expectation. You can kind of estimate that expectation with samples, as an example. Anyway, so in practice, there's a lot of circumstances where you don't actually need the exact posterior. All you need is to sample from it. And so as soon as you realize that, then it's kind of natural to try to find a generative model. So like a variational autoencoder is a natural choice here. So, so let me just kind of quickly show you how that looks. And then I'm going to kind of just quickly show you a couple of results, and then I'll open it up and we can dig into any of the particular directions that folks are interested in. So like basically the way to get from this general block diagram to a more specific one that actually encodes the VAE would be like replace this forward problem, the game solve, with the differentiable kind of implicit function theorem business we were talking about before. So we need it to be differentiable because I don't know who's ever trained a VAE before, and I'm not going to go through all the VAE math, but basically to train a VAE, you need to be able to differentiate kind of around all parts of the model. So anyway, we need to be able to differentiate from tau to theta. And then the inverse problem turns into this bottom part that's basically, so how does this work? If I give you an observation that's like some sensor measurement of some trajectories that the drivers drove, there will be a neural network whose weights we'll learn with gradient descent. This encoder, that's going to learn the mean and covariance of a normal distribution that's going to exist in a latent space, some arbitrary latent space. But there will be another neural net whose parameters phi will learn that maps that latent normally distributed variable into the game parameters, theta. So those will have some arbitrary non-normal distribution. Once we have a theta, we can pass it through the game solver and get a solution tau, which are, sensor model, this normal y given tau. The next box to the right will then tell us how likely a particular observation is. So basically, given all of these boxes, it's straightforward to kind of start writing down likelihoods of all of the variables given all the other ones, and you can basically train these encoder and decoder models. So I'm not going to tell you. Yeah. Quick question.
Just to clarify, is that top right block the decoder? Or like, so we covered VAEs or CVAs in this class, or
yeah.
If people have done homework one, then you'll be familiar. But just wanted to kind of draw that analogy, right? The top block is the decoder.
Yes, so the top left block where it says decoder NN, that's, I wish my mouse was showing, but it's not.
Oh, I see.
That's the decoder. So it's going from latent space Z to game parameters theta.
Oh, so I was thinking like that plus the thing on the right is like, you can lump that in as part of the.
Yes, yeah. Right. Plus, right. So yeah, basically if you go, so yeah, I guess that's proper. So like, how is this different from a normal VAE? The way it's different from a normal VAE is normally that decoder neural network would just directly map into the normal y given tau, or y given output of D, I guess. So it pretty much straight maps to the observations y. And what we've done is we've inserted this game solver in the middle, which forces a structure on theta. So it basically says, hey, we're like these things that are outputting from D phi, those are like specific things which have specific meaning to the like construction of the specific game. It's like they are, in this case, the like location in the plane where the human wants to drive to. And so that shows up as part of their objective in the game. And once you specify that, the game solver then tells you how likely a particular observation Y is. So like the entire top is the traditional decoder of the VAE. We've kind of partitioned it into a neural network and a game solver. And then the bottom is a standard encoder.
Gotcha. Thanks.
Yeah, great question. Okay. So how does this get used? Basically, I just take some observations. I can map it at runtime, map it through the trained encoder, sample a bunch of variables Z, sample a bunch of values of Z in the latent space from the normal that's encoded by Y, and then decode all those samples to theta on a, even on a CPU. This is like super fast, not so bad. So in our case, like the example I've been showing, just this intersection is like, well, anyway, that's the timing statistics, 1,000 samples, 7 milliseconds on a CPU, not so bad. Anyway, so I'll just kind of cut to the chase, show you some results, and then, like I said, I'm happy to dig into any specific directions or details according to whatever you guys would like to. So, so I mentioned the like planner that we used was basically the way it worked is we would sample, I don't know, 1,000 values of theta from the posterior. That's what I'm showing with these blue, like the cloud of blue things. So what's happening is like the blue cloud, actually I'll play the videos. I think it's going to pause here. Yeah, so basically, if you look at the bottom box, that's pointing to the kind of samples from the posterior P theta given Y. So given the recent history of where we've seen the human drive, we've now backed out of posterior and sampled from it and realized, oh, well, basically these samples cluster into 2 areas, and then the kind of green stars are the cluster centers, as an example. And then what our planner does is just then says, okay, well, let me consider 2 versions of the human driver, one where they're going to cluster center 1, the other where they're going to cluster center 2. So we kind of cloned the human driver into 2 like ghost versions, and solve a 3-player game where we, the robot in the bottom, are kind of trying to like minimize our expected cost over these 2 clusters. And like there's one human that's recovering behavior in cluster 1, the other human's recovering behavior in cluster 2, and we're just like hooking up the game so they don't interact with each other. So that's how we end up hooking up the planner. It's sort of not really the point of the paper, but just to illustrate how you could use this sort of posterior distribution in a generative way. What we end up doing is accounting for all the possibilities. And if you kind of now compare a little bit, like where are we compared to the MLE picture, which is what what Karen was showing before I started, and our work to date on this problem. When we're accounting for both the possibilities, when we're kind of accounting for the uncertainty in the posterior in this way, what it forces us to do is it forces us in this case to realize, hey, like we should probably slow down because I don't know what these guys are going to do, and I need to avoid collision with both versions because I don't know which one it is. So it forces us to slow down, which is going to happen as soon as I unpause the video. And you'll see that basically in the left, we're going to end up like slowing down and like very neatly like only like making it through once we realize like which direction they're actually going. And then the MLE side, it's not going to slow down because it's just going to be committing to the maximum likelihood guess, which is the thing that's like right now it's like in the bottom. Gosh, oh yeah, here's my mouse. Okay, right there. So that's like what our MLE planner currently, like that's the MLE for where it thinks the human's going. So so that's why this red line is going here. And then the green that we're showing is the ground truth. What the human actually wants is to go over here. So early on, like basically the MLE planner can't figure out what the hell's going on, so it's bad. And then as I unpause, you see like basically we had to make this late avoidance maneuver to avoid the collision, super unsafe. Whereas I'll just show it again, like anyway, on the left we're slowing down just enough so that we don't have to make this late avoidance maneuver. On the right, we can't do that basically. Okay. This also totally scales to more players. There's a little bit of a caveat I'll ignore, but generally speaking, the formulation and everything works for more than 2 players. So here I'm kind of showing you one robot interacting with 3 humans. And so you can kind of do that too. It's a bit messier to like see all of the interactions here, but at least hopefully this convinces you that the framework applies in more substantial examples too. And that's basically it. So that's the types of things you can do with this kind of variational inverse formulation of the problem. There's a lot of guts that I'm like nuts and bolts that I'm avoiding here, but I'm happy to open it up for questions now. So maybe let me stop the screen share and we can just go kind of freestyle here.
Thank you. Yeah, and any questions in the room or on Zoom?
Yeah, I thought the example was super cool, and I was curious about like in the example you have like 2 specific trajectories that you were kind of accounting for the other agent. Like it was either going to go forward or turn right, left. But is that like you have 2 discrete trajectories, but is there like does it get more continuous? Like, are there cases where like the possible numbers of trajectories increases, and like how does the decoder plus like differentiable game solver pipeline account for maybe higher numbers of like possible trajectories? Like,
yeah, that's a great question. So let me kind of just rephrase it slightly just to make sure I get it. But I think the question is essentially asking like, what if I don't know a priori how many sort of discrete modes there are going to be to the posterior? How do I handle that? So I think the naive answer, at least the one that I have in my head, which we haven't tested, so take it with a huge grain of salt, is you could just sample arbitrary number. Like let's say you sample 1,000 times from the posterior. Like as long as there are less than 1,000 modes or whatever that distribution looks like, sample to your heart's content to get approximation of the distribution that's kind of finitely many samples, and then basically solve that problem with that many clones of the human. And now that's like, now we're talking about a game with 1,000 players. 999 of them don't interact. So that has a particular structure to it. So it's a wild number of players, but it's not necessarily a wildly complicated game just because the interactions are only kind of, it's sort of like a hub and spoke kind of interaction. So I'll say this, like I said, we haven't tested it, but we do have some work that's basically coming up with like a splitting method. I don't know, like for folks who have taken optimization, like if you've seen the ADMM, it's based on that. But you can kind of design, sometimes you can split optimization problems by introducing kind of dummy variables in clever ways and solving them, kind of solving sub-problems in parallel and recombining solutions. And so we've cooked up a version of that kind of algorithm for a related class of games. And I strongly suspect we could just use exactly that algorithm for this problem, but we haven't done it. So that's the caveat.
Okay, thanks.
Yeah.
Second question?
Yeah, probably related to the answer may be the same. But I guess if you're doing the clustering approach, which would be more sample efficient, like, is that relying on some sort of smoothness in the solver? Like, what happens if a cluster boundary kind of crosses you get like different modes in the actual outcome trajectories? And is there any way to like do clustering in a way that's aware of how those game parameters impact, like doing clustering kind of in outcome trajectory space, lifting it back to game space?
That's a great question. Yeah, that's a really great question. It's not something I've thought about, so I guess I can't really give you I don't have a great answer off the top of my head for you, but I guess what I'll say is my gut feeling is that there's some chicken and egg problem, I think, to what you're describing. Like if I knew what I don't know what the equilibrium trajectories will be until I solve the game. And so it's hard for me to come up with a way to cluster in the space of trajectories, of equilibrium trajectories, until I actually can, compute them and then measure the distance. So I think, if you go and do all of that, if you're going and finding all of the equilibria before you cluster, then I'm not sure what the point of clustering was, because then you might as well just use all of the information. So anyway, that's kind of where my head is going, but I guess I don't really have a great answer for you.
I've kind of maybe a simpler question, but what if you were running two ego agents, two robots running the CVA model in the same environment? How does that work? Do they consider each other? Like, do you just?
Yeah, so it's funny. Like when my student Shinji, when he presents this this work, he has a good diagram that I should probably have included, which is like, so think about all of this as this is what's going on in the robot's head. In this example I was showing. So like, so it's like, what's the robot doing? The robot like doesn't know what the human's objective is. So it's looking at the recent history and trying to cook up a posterior for what it thinks the human's trying to do. If there were two robots or two humans for that matter, this sort of, like the important point is that this is a process that can go on in any decision maker's head. And it's basically trying to fit parameters of a model of how the other guy's going to behave. So if there's two robots, like this is something that could be going on in both of their heads independently. And there's all kinds of questions that come up, like, oh well, what would the closed loop behavior look like if everybody was doing that, right? So I think we and other people have definitely like acknowledged and identified some of the core problems that happen there. Like the first obvious one is like there's kind of an equilibrium alignment issue. So if there's multiple equilibria of the game, like if kind of the different players decide on different ones, then they could have some coordination problem, like everybody needs to go right in order to avoid collision, like around a roundabout or something, but or left. But if somebody goes right and the other one goes left, then they'll hit each other. Right, so sort of there's some classic kind of toy examples that illustrate those issues, and we really haven't. Like this is a pretty unexplored area, I would say.
Cool. Any other questions? Our lecture finishes at 11:20, so we have to wrap up. But if there's any last quick questions,
A quick one. Just like in the network diagram you had, I didn't see any like conditional input data. Stuff like map context, does that come in both in like the cost function as part of the game solver and also like the encoder inputs, or where does like additional context come in?
Oh yeah. So we didn't model any additional conditional context. That I think that could have gone into both. Good question. I guess it could have gone into both the encoder and the decoder, but to be honest, it's not something we've like really bothered playing with. Yeah.
cool. With that, we'll thank our speaker again. Yeah, I really enjoyed your talk, and thanks again for your time. And I have actually other questions, so I might follow up.
Yeah,
You later,
Anytime.
related to conditional input, like on context and all that. So
Yeah.
So yeah, anyway, thanks for your time.
Let me also quick drop my email into the
Yes.
chat here, just so like I guess it's recorded so everybody will get it. Yeah, there's my email. So anybody wants to talk about any of this stuff, happy, just drop me a line.
Okay, yeah, I'll share the email with that class as well. Okay.
Alrighty.
Thanks, David.
Alrighty. Yeah.